Swayam Prabha. Digital India. Educated India.
So in the lab, so another important aspect of operating system is that we need to do task switching. So we already had some notion of what is a layered operating system. So there are 4 layers. Normally in an operating system we could have up to 4 layers, a kernel, then there can be some system programs, then there could be development programs like compilers, etc., and then the user application program. If you really want to build a capability based operating system, right, we need to assign certain privilege levels for each of these programs or each of these objects, if we could say. So we will have a privilege level 0 for the kernel, privilege level 1 for the system software like device drivers, etc., privilege level 2 for the system software like compilers, and privilege level 3 or development softwares like compilers, and privilege level 3 for this. That means if you look at a processor, it basically works across 4 privilege levels. So there will be a context switch from the kernel to a middle layer to another layer. So the processor can work in one of the 4 privilege levels, namely privilege level 0, privilege level 1, 2 and 3. Okay. Now, so a task which is nothing but a process which is a program in execution has to basically execute in one of these privilege levels, and what we are trying to teach through this 4th assignment is how in the Intel platform, how do we move from privilege level 0 to 1, 1 to 2, 2 to 3, and then there is always a reason for us to basically be in one privilege level and try to access something else in some other privilege level. For example, simple hello world, I want to execute printf. A simple matrix multiplication, I want to do a malloc, right. So when I am executing a C program, there is a need for me to go and have a system call. I am going to have a system call, basically wanting the operating system to satisfy some needs of this program. So there is always a necessity for me to be at a higher level and switch down to a lower level and come back to that higher level, right. Then there are other needs, like for example, let us take setting password, right. So you are updating your password, right, in your Unix system. Where does your password get stored? / etc / password, okay. So / etc / password is the file. In / etc directory there is the password file. That password file, can you write into that password file? No, but you are writing into the password file, because you say password and you enter a new password, it gets written into that file. Though that file by principle is only editable by the root or the super user, you are able to now, as a normal user, you are able to go and update that file and come back. Okay. That means even though I have a very privileged object inside my operating system, there is a need for a less privileged process to come and manipulate and do something, but with subject to certain rules and regulations. What is the rule and regulation? A single rule and for updating your password, you can go and change your password there, right, your shadow password. Basically password is not stored like that, it is basically stored, it is hashed and stored. So you can go and change your hash of your line in that particular file. You can't go and change his line. So I have a selected way, I have a selective way of permitting you to go and change an object which is at a very higher privilege level. Do you understand this, right? And so the underlying architecture should have certain hardware mechanism to allow you to do this, right. So this is what we are trying to cover in this task switching, right. This understanding is quite necessary, because tomorrow when you look at operating systems, then you will face, this is a question which would be asked, and then the answer is not just software. The answer is both software plus hardware together. If you want a really foolproof mechanism for password updation, then it is, in my opinion, it is going to be a careful mixture of hardware and software together. and as a part of this course we need to teach you what is that hardware component. Are you able to follow? Am I setting the stage correct? Okay. Now, so all is about task. I have a task, this task is executing at privilege 0, I want to escalate its privilege or demote its privilege to 3, 3 has lesser privilege than this. Something is working at 3, I want to escalate its privilege to 0, vice versa. So that is what this entire assignment is about. We have made it very short so that we have given you a lot more templates so that you can complete it within a week. Okay. Just spend this Saturday, Sunday and you can finish it off. It's very going to be very simple. We are not putting a lot of pressure on that. Okay. But please understand this. So when I have a task, I want to keep executing the task, and there is a need to switch from one task to another task, which is called the context switch, right. So I stop this task and start executing this task, and if this context switch is not done with enough amount of security, then we may land up with lot of issues in information security. This becomes potentially a threat to information security, right. If you look at all the attacks that have happened in the past, many of them are because of this problems in switching between one function to another function or one task to another task. Okay. Now let us go and study this in great detail, how Intel has put certain security mechanisms for task switching. Now first and foremost, let us understand that I have a task, I am switching into another task, so what is it that I need to save? And that is called the context of the task. That context we have already defined. What is the context of a process? It is the minimum amount of information that is necessary to restart the task from exactly the point where it has stopped, and that is what we mean by this mechanism. So let us see what is it. So I will just quickly go into that, what you call as. So this is the, whatever you see here, this is the task state segment, right. This task state segment basically has this. So it has a place for all your general purpose registers. Look at this index 40, etc. It has a place for all your general purpose registers, EAX, ECX, EDS, EBX, ESP, EBP, ESI, EDA, right. Then it has a place for your E flags, because your flags are very important, right. So I might have done an add operation, and then I would have done a compare operation, and then there would have been a counter switch. Next time I want to jump on 0. Okay, the flag is very important for me to save. Correct? Why should we save the flag? I have done a compare operation. Next time I say JZ, before the JZ and after the compare there was a context switch. Then I need to save the flags. Right? So flags are to be saved. The instruction pointer of the next instruction to be executed, that is saved here, EIP if you look at. And as I told you, your CR3 is also saved, because every processor can have its own base table. So your CR3 is also saved there. Then the content of all your GS, FS, DS, SS, CS, ES, all these are saved. And then I could have something called a GDT, that is a global descriptor table. I will have a local descriptor table for some of my local memory accesses, which is created by the operating system. That LDT segment selector is also saved, which will point you to the LDT where the segments are there. Okay. So other than that, please look that there are 3 stack segments as SS0, SS1, SS2. Basically ESP0, ESP1, ESP2, there are stack pointers of them, and those are basically created. Why it is created? Because when I am a program and suddenly I want to go to a task 0, right, task 0, it is an interrupt service routine, right. Now what stack will the task 0 use? It will not use this 3 stack. I do not want it to use, I am a privilege level 3 code, I am executing and I am having an SSP ESP3 stack, a stack with privilege level, a stack whose segment is at privilege level 3. I do not want my other program to use the same stack, because when it comes out, then some information of that stack can be leaked, because if it is using the same stack, that means what is going to happen? It is going to write into your data privilege 3 data segment, and then any other fellow can come and access this privilege 3 data segment. You are able to understand. So if I am a privilege tree and I am calling a kernel level routine, it also uses the same privilege tree stack. When that kernel level routine is executing, there can be a context switch and another privilege tree level code can start accessing, and it can go now and screw up the kernel level 3 data structure. You are getting this. So when I get an interrupt, for example, when I get an interrupt, right, and my interrupt service routine is at privilege level 0, it will start using the privilege level 0 stack and not the privilege level 3 stack. So when a process has a system call or it has a trap, the trap routine or the system call, whatever that routine, if it is going to execute at say a lower privilege level, that will use the stack of the lower privilege level. Okay, you are getting this, right? So that is why when you are setting up this task state segment, you create a stack for privilege 0, privilege 1 and privilege 2, because in case that program that you are executing, which is privilege level k, wants to have a kernel level service or a system level service of a lower privilege level, the stack that service will use is not your stack but the stack that is given here. So the entire task state segment is set up by whom? By the operating system. So when you are spawning a task, immediately I create one segment for you like this, right, and then so this segment, whenever there is a context switch, when you are moving out, the latest value of all these things will be saved in that segment. So there are two processes working. When he is working, after he finishes, his latest value will be stored in this task segment, and we go to the next fellow, we load all the things from his task state segment and start executing. After he finishes, say round robin, he finishes, that state will be stored in his task state segment and he should restart, we will reload from his task state segment and start executing it, like this. So this is basically what we call as the process control block. From the operating system point of view, this TSS is basically called as a what? A process control block. This is an hardware image of a process control block. Are you able to follow? Yes? Yes or no? Okay. So now what happens is, so how do we switch from one task to another? So there are two levels of things. First is there is something called a task gate, right? The task gate is a part of your GDT or LDT or IDT. Okay. Task gate is a part of your global descriptor, it is another descriptor, like another segment descriptor, and what it will store, there is a descriptor privilege level there, DPL, there is a present bit, of course that should be 1, and then there is a type 00101, that essentially means this is a task gate, and then there is a selector. Okay. So there is a selector here. This selector will tell you which task state segment you need to go. Okay, right. Now how will the selector look? So this is the DSS descriptor, this will tell you where is the base address. This is a normal segment selector, right. It will tell you what is the base address of that TSS, that 104 bytes, and then what is the limit, then the type, please note it should be 010B1, and then you have a DPL, and this is the granularity bit, and this is the limit. So a TSS descriptor will be as same as the normal descriptor. So this is how we access. Now there is a task gate. So if I want to jump to another privilege level, I jump on this task gate, right. This task gate will point to a TSS descriptor, because this is a task gate, right. This task gate will point to a TSS descriptor. That TSS descriptor will point to a basic address of 104 bytes. So from that 104 bytes, what you do, you copy EAX, ECX, all these things, copy, set all these things, and then your EIP will also be copied. So you will start executing the other routine. And what will be the privilege level of this? There is a CS here, you have jumped to this CS has a privilege level. This is a CS is nothing but a code segment selector, right? So it has a privilege level, so you jump to the third privilege level. From third to 2 or 1 or 0, whatever is the privilege level of the CS, you get into it. Okay? So essentially that means you have a TSS for a privilege level 0 stack, privilege level 1 stack and privilege level 2 stack and 3 stack, right? You could have TSS for it, and you will have a corresponding TSS descriptor, then you will have corresponding task gate which will be pointing to the TSS descriptor. Now what you need to do if you want to go to that task, basically do what? You do a task gate, you jump to that task gate in a LDT or GDT, you jump on the task, jump the task date selector, if jump on that selector, if the task gate is stored at say 0x16, right, you just say jump 0x16 or call 0x16, immediately that will now come to the, if that is a task gate, it will point to a TSS descriptor, it will come to the TSS descriptor, from the TSS descriptor it will basically upload your new task and you will start executing from where that EIP in the TSS is. TSS has an EIP, you will start executing with the privilege level of what that CS segment has. So I go from 0 to 3 like this, or 3 to 0 back like this. Are you able to follow? Yes? Yes or no? So this is something like this. 0x79 will store a TSS task switch. So you just say 0x79 and that will point to a TSS segment selector, let it be a 0x78, and then you go to 0x78 or whatever and you basically go to the TSS segment, upload everything and start executing. Okay, while doing this we also has to make sure that if I am a third, there is a DPL, right, there is a descriptor privilege level for this task gate and also for this task descriptor. All of them should be, as the descriptor privilege level, like the task gate should have 3 means, then a 3, 2, 1 or 0 can jump to it. If I put it 2, that means a 3 level process cannot jump to this. Okay. So that is how I adjust the value of the DPLs of the task gate and task descriptor to basically tell who can come and jump to me, who can come and use me. I have that level of privilege also. Okay. So this is the way I can switch from one task to another. And now let me introduce one very important concept. Suppose what happens when there is an interrupt? What happens when there is an interrupt? Immediately something is loaded on the stack and then you go to the interrupt service routine. You are right. Now when there is a privilege 3 code and I have a stack fault, that is also in trap, right? That will not cause any problem because whatever I am going to push is in a privilege level 0 stack. My privilege level 3 stack is what is getting affected, there is a stock fault. Privilege level 3 stack, there is a privilege level 0, there is another privilege level 0 stack. So privilege level 3 stack something happens, but I am going to only update the privilege level 0 stack, correct? But if a privilege level 0 code itself has a stack fault, that means I am trying, when there is a fault, I am trying to load, when there is a trap, I am trying to load something and then calling the interrupt service routine. So there are 3 steps. There is a trap that has occurred, then I am loading something into the stack and then calling the interrupt routine. So hardware does 3 steps there. While I am trying to load into the stack itself, I land up with another problem, then that is called a double fault. It is called a double fault. Okay. Please understand, I am a process, I have a trap, I encounter a trap. As a part of servicing this trap, what I should do, I push something into the stack and then call the interrupt service routine. The trap service routine does something and then returns back. when I am trying to push something before even calling the interrupt service routine, after I have got a trap and before calling the interrupt service routine, when I am trying to push something into the stack, if there is another problem that is coming, that is called a double fault. You understand? So what is a double fault? I have asked, n times I have asked in the interview for so many people in last 17 years of my stay at IIT Madras. Everybody says that when the interrupt service routine is executing, the interrupt service routine lands up with another interrupt, then it is a double fault. No. When the interrupt service routine starts executing, it is another process by itself. It creates a fault, then it is its fault. It is not a double fault. I have an interrupt fault, I have a fault. When I am trying to process that fault before even calling the interrupt service routine, I will end up with another fault, then it is called a double fault. There is one very good instance, a privilege level 0 stack, that is a privilege level 0 code which is trying to execute which has a stack fault, and the interrupt service routine is also privilege level 0 and they share the stack essentially. Then I will end up with a stack fault. When there is a double fault, what I can do? I have to do it completely, some other process has to come and handle. I can't handle this fault like a function call, because function call will need a stack and my stack is ruined, right. So I have to go and have a trap, I have to go and call an entirely different process which uses an entirely different stack to handle this. Are you able to get this? So that is one of the reason in the IDT, right, in the interrupt descriptor table, I will have lot of interrupt gates / trap gates, but for at least one fault I need to have a task gate which warrants that if this interrupt comes, I need to completely do a task switching, right. Yes, I have to do completely, because, and one of the prominent cases for that, you could have other device drivers also as a part of it, but one of the prominent cases for this is the double fault. Because double fault as of today, when we perceive, it is because the stack got corrupted, and if the stack got corrupted, I cannot use an interrupt or a trap gate to solve it, because interrupt and trap gate heavily relies upon the stack again. So that is the reason I will have a double fault which will take you to an entire different process, and that process will start servicing this fault. So that is why we try and use a task gate in your IDT. Are you able to follow? Please understand and appreciate what is a double fault. It is not an interrupt service routine creating another fault, it is not double. There is a subtle difference here, I hope you followed. So when I do a call, what is the difference between a jump and a call? Call I have to return back. When I do a call on as a task switch, I call some other process, that means I completely come out and he executes. After he finishes and he returns, I have to come back here. Please note that in this there is a previous task link at 0. If you look at 0 there is a previous task link. This will point to the previous task state segment. Yes.
So though two tasks have the same privilege level, they are still different, right? So
they are still different, yes.
Isn't there like inter-process protection problem here?
So that's a good question, but as of now, yes, there can be an inter-process protection. How do we handle that? We'll just basically see after this step. But now, can you see that if I do a call, my previous link will be stored here. So after you return, automatically this previous task link will go there and it will load the context of it. Okay, so when I do nested calls, I move from one task to another task as a nested call. Please note that this previous task link will be updated so that I could come back to the previous task. Okay, so that's also very important. Okay, so this is one. So with this amount of data, now let us go and look at one more. This stops there. Okay, one more thing is where is call gate? Maybe it's not there, I will just basically explain. So another thing is, one of the entries that you can have in your descriptor table, your GDT, LDT, is that of a call gate. In that call gate, what you have is that you basically say that you give a code segment and then index within that code segment, right. You give a code segment and index within a code segment. Now you say a privilege level 3 he can call this, if he calls this then what he can do, he can go and execute that code from that index only, right, followed. So and but that code can be in whatever lesser privilege levels like. So this helps in the context of a password. So I want to change the password, so I type password, this will point to me a process through a call gate mechanism and I go and execute that process there, right, but I am enabled to execute that process of a higher privilege and which will, and that alone will execute. I can't have an influence on that process, it will execute and return back, right. So essentially I am saying I am privilege level 3, I am poor, he is privilege 0 etc. password, I can't even touch him, but you are a nice man, so please go and deposit that, you tell the call gate, right. The call gate will get some routine which will go and deposit and come. So the call gate will tell me, or vice versa, the call gate CALLGAT, not toothbrush, okay. So CALLGAT, call gate, okay. That call gate will tell me that, hey, you want to do this action, you can do, you tell me, I will do, you will not do, but you can tell me and I will do it for you. So what you tell him, hey, this is my new password, go and save it, this call gate, you tell the call gate through the call gate and that fellow will take your data, he will and give it. So call gate is another mechanism where a privilege level 3 code can go and access a privilege level 0 segment through a privilege level 0 code which is accessed through the call gate. Okay, so this gives, without doing all this task switching is essentially, you see, it is a very shitty thing, correct. I have to do so many things there to get this task switched. I have to go to one task gate, then to one TSS descriptor, then to TSS, and then from there load everything here, store everything currently, load the new thing and then start, okay. It one Varsha will over, one full 1 year will get over. So that is a very heavily intensive, compute intensive task, okay. So call gate gives you an very good advantage of enhancing your privilege level, okay. Is it fine? So you will also implement call gate here, okay. Now I will go to this in the lab. See please note, now there is a PL0 kernel, okay. I will do one small story here completely, like how we jump across. Then there are blue color PL1, then there are some PL2s, then there are lot of PL3s, okay. Now when the PL0 starts executing, okay, now there is a GDT in which there are some code segments, stack segment, blah blah blah. These are all privilege level 0 segments, okay. These are all privilege level 0 segments, and then there is one task state segment for the privilege level 0 code. So the GDT ends here, this is the GDT, then there is a task state segment. So there is a task gate here which points to a TSS descriptor which in turn points to this, okay. All these are here. Now what happens is when the kernel comes, it starts executing, right. It also makes, there is a execution call, there is an instruction called LTR which is a privileged instruction, and this LTR, it will store the index of this task gate. Let this be stored at 0x20 or something, so I will store 0x20 here. This will store the index of the task gate. So now PL0 code is executing, its context is available in this TSS, because the task gate points to this TSS descriptor which is in the GDT, and that will point to this TSS here, and this is given. Okay. Okay. Now I want to go, let us say I want to go to a PL3 code. Okay. Right? Are you able to follow what I am saying? So immediately what this fellow will do, he will set up an LDT for this one. And then in the LDT, this is a local descriptor table, he will create the CS, DS, SS, right, and then he will put one task gate, one TSS descriptor, and then another TSS for him in the same memory. This will point to this for PL3, this PL3 process. And then he will have a task gate. Okay. So he will do this, and this fellow will jump on this task gate. Let us say this is 0x40 or something. He will jump on this 0x41, the LDT, right. He will jump on this task gate. In this task gate, you would have initialized the EIP here, and it will start executing from the TAP point. You are getting this? Yes?
We can't have TSS in LDT.
Huh?
We can't have TSS descriptor in LDT.
You can't have? TG only you can have, right?
TP.
Huh?
Yeah, you can't have
TSS descriptor. Okay, acha, let that TSS be here. Okay. But the TG I can have. TG I can have, only TSS. So, okay. So this TG will be pointing to this, and the TSS will be somewhere in the middle. Okay. Now this fellow will be executing, and then he wants to come back. What he just again say jump back or return. When it returns back, so when I do this jump, your LTR will now point to this TG. Now your LTR will become 0x40 when this is executed. When it does back a return, it will become LX020. When I go from this process to this process, I will save all the details of this fellow, and then load all the details from this TSS and start executing. Okay, right? Now please note that this is also in privilege level 0, this is also in privilege level 0 of memory. The PL3 process which I am executing, this process namely, cannot go and adjust the value of this LDT, because this is, it can use the value of this, it cannot change. So essentially it can only access the DS, SS, T, etc., only the descriptors that are stored here, those memory only it can access, it cannot access anything more than that, because every memory access is governed through one descriptor, and that descriptor has a base and limit. So the privilege 3 process will only use this, and that's all. And the TSS also will have a pointer to a page table, it can use only those pages. It cannot go and touch any part of, for example, it cannot touch this GDT, because none of the descriptors in the LDT, right, points to the GDT, includes the GDT. So I can't go and change anything. As a PL3 process, I can't go and change anything in the GDT, because I should have a segment descriptor here with privilege level 3, which should allow, which includes the addresses where the GDT is stored, and that will not be there. So I can't go and change the GDT. Got this? Are you able to follow? Yes or no? Yes? Okay. Now what happens? Now I come back here again. Now another PL3 we want to start. Let us say green fellow PL3. Again this fellow will put another LDT entry. Again there will be CS, DS, DS wala. There will be a TG wala. Then there will be a TSS, and there will be a TSS descriptor for that also in the GDT. So when I come this, I will just start executing with this EIP in this TSS, and I will execute and again come back. Now this process can touch only the data segments that are available in this LDT, because all here they are all PL0, all here are only PL3. It cannot access this because the LDTR register can be changed only by an LLDT instruction which is already privileged. So I can't go and adjust my LDT. So the LDT is basically given by the kernel. I can use only the segments that are available, and I adjust in such a way that these two doesn't coincide. So by using an LDT, a privileged level 3 process, both are privileged level 3 process, but this cannot access that fellow's memory and that fellow cannot access this fellow memory. Yes?
What about the stacks?
Each will have its own stack here. This SS, this SS. So any memory I can touch only I can use only the descriptors that is given in my LDT. I can't use any of the descriptors in the GDT. Why? Because they are all privilege level zeros. I can use only the descriptor in my LDT, and I can't change my LDT. If I want to change my LDT, go back to the operating system. So this type of a mechanism gives absolute isolation between two processes that are running. Correct? So this is how. So then when I move out, again I save everything in this task state segment, and then I again load everything from this the PL0 task state segment. Again I go. Now I want to restart this, again I jump to this and then call this and then go back. So are you able to follow? See how I move from this. So a notion of an LDT, and that the LDT can be privileged and your LDTR is a privileged register. So thus gives us a way by which I could have inter-process protection between several processes of privilege level 3. So this is another thing that you need to keep in mind. Okay. So your GDT, and there is a GDT for the entire system, there is a per process LDT, and the per process LDT also is created by the operating system, and it is put in an area of the maximum privilege level so that nobody can change it. Okay, are you able to follow? Any doubts? So with this I think all my lecture with respect to lab is over, so if you have any doubts you can ask me. Okay.